Okay, so without further ado, I'm going to write down and present to you what's called the Newton's law of universal gravitation. Okay, and then we're going to understand how Newton can come up with it. Okay, so first of all, right, it is written like this, and we'll dissect every component of it. But this is something you want to put in a box and you want to commit it to memory. Okay, so what it really means, right? But the first thing I want to give you a caveat is you really want to put this right underneath your box, is this is about the magnitude of the force. Okay, magnitude, underline that, right? Because it says nothing about the direction. The direction is said separately. The direction is just each has a gravitational force towards each other. So what does the law say? The law says this. I'll put that in proper words in a second, but I'll just say that in words first. If you have any mass, right? You have a first mass. You can call it M1 and M2. Sometimes, I told you many times I don't like subscripts that much. It makes things very confusing and hard to read in terms of equations. If I do write subscripts, I go all the way. I actually write, full English words to actually know what I mean by that. But yeah, I don't like the in-between one. So sometimes it will put little m and big M, right? So it implies sometimes one mass is larger than other. But in this special case, so I, in some sense, like having that because it emphasizes the fact that they don't have to be one large mass and one small mass, just two mass, right? To emphasize that further, let's say it's just two apples. Anything with mass, it says it will produce a force. Okay, so you could have called that M1, M2, big M, little m. Either way, the key is to understand what it means, right? And they will produce a force in a direction that attracts each other. So it's called universal gravitation because universally, anything with mass, everything will attract each other. So what happens if I have a third apple? M3. Now the law suddenly says nothing about that. Or does it? Well, it does. It says everything will attract each other. So this will also attract this. So M3 will pull M1 towards that way, and M2 will pull M1 towards that way. So M1 actually experiences two non-contact forces. All right. So what is the net force? Well, you know how to add arrows, right? So you can resolve these into vectors, into its XY components. And now add it. If I give you numbers, I haven't give you numbers yet, but if you, basically the problems, a big part of the problems in this chapter is nothing new. It's all vectors. So if you know how to add vectors, it's really just back to day one in chapter one. If you know how to add arrows, you're set for 50% of the course. And then the other 50% is circular motion, which we'll get to, right? And of course, this guy will also experience a part of the gravitational force here. It's a universal gravitational force this way, a universal gravitational force by M3. This guy experiences a universal gravitational force by M1. This also experiences a universal gravitational force by M2. So these are the free body diagram. I've just drawn the free body diagrams, the three free body diagrams of these three apples, right? What if you have a fourth one? They all will attract each other. So property number one is it's universally attractive. Okay, so in some sense, right, the direction is universally, yeah, maybe I'll put that below the magnitude. So the first comment is the magnitude is this, and the direction is universally attractive. Okay, so this is let's put this law in words before I explain what it means, right? So the law says that for any two objects with mass, there will be an attractive force on each object. So as you saw, right, apple 1 and apple 2, they both experience a force and it's attractive towards each object. So on each object towards the other. With the magnitude, I could write with a magnitude of G times M1 times M2 over R squared. I could write that, but let's write that in words, fully in words, since we're committed to that. Proportional to both their masses and inversely proportional to their separation distance square, or the square of their separation distance. Okay, so sometimes I'll call this the separation, sometimes I'll call it the distance. Yeah, so that's the law in words. As you can see, writing this in words is much longer, but writing it in equation is much shorter. Okay, now be careful, there is no negative signs anywhere over here if you write it in magnitude, because magnitude has to be positive. You could write it as a vector form, and I'll put it over here, but we won't talk about it too much. Okay. So this is the vector form of it, the vector form of the law, and there is a negative over here. And what that means, we'll see if we have time to talk about it. But most of the time, you don't really need to do this if you do magnitude and direction separately. Okay, so if you understand how to add vectors, that is usually the easier way for a lot of purposes. Okay, all right. So what does it mean, right? So it says this is the magnitude of it. So if I have an apple over here with M and capital M, this guy will experience a force this way. This guy will experience a force this way. And by Newton's third law, we know that they are equal. Okay, so we don't need to worry about the direction. It's because we've talked about the direction already. It's universally attractive. Now we just have to worry about the magnitude. So there's no negative signs with regard to the magnitude. Just talk about how long this is. We talked about the direction already. And how long or how strong is this gravitational force? It's proportional to this. So let's label these things. So this is the mass of the first object. This is the mass of the second object. This is the separation or the distance. As you see, there's a square, and this is a constant. So it's proportional to everything over here. And this constant is called Newton's universal gravitational constant. Okay, so lots to unpack here. So if this is a constant, that means it is proportional to this thing, right? So remember about proportionality. If you have a constant times something, it is proportional to it. So it's proportional to this, it's proportional to this. And if it's the constant divided by something, it's inversely proportional to it. So if one of the apple has a larger mass, it will create a larger gravitational attraction, okay? And of course, it's proportional to both masses, and it's also proportional to the inversely proportional to the separation distance, which means if you increase the distance, it will decrease the force. But there's a square over here. Okay, so Newton came up with this, and he realized everything, not only on Earth, but everything throughout the solar system satisfies this. Okay, how does he come up with it? We'll basically talk about that. Okay. So comments on this. If you're ever asked about the law, you can either write just this part, you can write down this and then say the direction is universally attractive, the magnitude is given by this, but make sure you also label what do you mean by the variables, because this you can label it with S if you want for separation, label it with D if you want, but it's the separation distance between the two, often written in R, but yeah, so that's the version of the law. So now you can see how Newton's third law take effect, because what will this guy experience? Well, this guy will experience a force that is gmm over r squared, right? And this also experiences a force gmm over r squared. one of the mass has to be his own mass, and the other mass is what's causing it. So here, if you can think about it as one of them as the mass of itself, and the other thing as the mass that's causing it. So this guy, its own mass is capital M, and what's causing it is little m. So you see that if you apply the law, then they have exactly the same magnitude, and they have opposite direction. So you see Newton's third law is also built into this, and that also answers a question of the one thing we raised while earlier is for the Earth and the Moon, right? Which one attracts which one with a larger force, and it's equal because this one attracts it with gmm over r square, where r is the distance. Oh, if you have an extended object, where should you start counting the distance? Should I start counting from the surface, or from the close end of the surface, or the far end of the surface, or from the center? What do you think? Well, you probably guessed from the center. Everything is from the center of mass. So this is all, the center of mass is sometimes also called the center of gravity, right? Same thing, and it's for that reason. So the moon will experience this force, the Earth will experience g m over r square, and you see it really doesn't matter which way you put the m, as long as you know one of the m is its own mass, one of the m is the other mass that is attracting you, and they're of the same magnitude. Okay.